All right, good afternoon. So it's a great pleasure for the Wednesday Colloquium. I'd like to introduce the speaker, Libai Huang. I think Libai and I, we go back to kindergarten. Not quite. So she is our common interest was in the development of ultrafast microscopy, and in her specialty, what she will also talk about is on transport in quantum dynamics in molecular and quantum materials. This is where she's actually a true leader in the field and very widely recognized for a very unique development of techniques she will probably present to us. Libai got her Bachelor of Science at Peking University in chemistry. For full disclosure, we are both chemists, so there are others in the room, so you're not alone. Then she got her PhD at Rochester, and then a postdoc at Argonne National Lab, and then she went on the faculty at Purdue, where she's leading actually a large center also on quantum photonics. And with that, let's welcome Libai.
Thank you, Markus.
And if you give a good talk, we'll give you one of our department calendars.
Oh, okay. Then I would try to do my best to win that prize. Thank you, Markus, for the kind introduction and for the invitation to Boulder, a beautiful place. And in fact, I guess, Markus and I did go back to kindergarten in the sense of scientific developmenthood, I suppose, on the early days of, how to combine spectroscopy, ultrafast spectroscopy with microscopy. And today I'm going to talk to you about some of the sort of the newer things we have been doing. And by the way, I consider this to be an incredible honor to be able to present a colloquium in physics at JULA of all places, because all my trainings are in chemistry, as Markus mentioned, but we are very interested in some of these fundamental questions, I think, that are sort of across fields. So I hope that today I can show you some how we think about, understanding many-body interaction in complex systems. And in particular, the quantum particle choice is going to be excitons. And excitons are these excited quasi-particle exist in semiconductor or molecular material. And to the sort of simplistic view, you can think of them as an artificial hydrogen atom that is residing in molecular or solid-state semiconductor lattices. And when you excite, say, how it works is that when you photoexcite a electron, say, from the valence band to the conduction band, and you left behind a hole in the valence band, and then because of the Coulomb interaction between this positive hole and the negative charge electron, essentially you can write down the potential energy for this quasi-particle, very, very similar in ways of Coulomb interaction between a proton and electron hydrogen atom. The only difference is that this Coulomb interaction is going to be normalized by the dielectric constant of your materials. And so if you solve the Schrodinger equation, then you would get a wave function that very much reminiscent of these hydrogen atoms. And so excitons can be residing in many different types of systems. And in my lab, we look at all different kinds, starting from molecular system where you have very low dielectric constant, so you have very strongly binding excitons, to some of these two-dimensional semiconductors where you have stronger dielectric screening, and also as well as in quantum dot. Today, I'm going to focus mostly on these two-dimensional semiconductors, in particular this transition metal dichalcogenide. And the special thing about this two-dimensional semiconductor is that they are single or few atom thick, so that while the screening epsilon is very large in plane, but out of plane is vacuum, so it's very weak screening. So you would have this very strongly bound exciton as well, and they are highly depending on how you layer them. Like so the dielectric environment can strongly affect how these exciton behave, and so these excitons then are going to be our quantum particle of choice, and the question is how we can manipulate them, and in particular their interaction in these solid-state systems. And just kind of give some visualization of like how this exciton wave function looks like. And as I mentioned, that they are sort of, you can think of them as like an artificial hydrogen atom, and you can see that this is a calculation done on a single layer tungsten diselenide. And you can see that you do see like this orbital or like this wave function very much like your hydrogen orbital, like 1s, 2p, and so on, right? And I guess the key difference is because of the dielectric screening, then you're going to have a wave function that is more delocalized compared to your hydrogen atom. So in this particular case, they are on the orders of 1 to few nanometers depending on the excitonic states. And so one of the things that we are very interested in this exciton is that are twofold. So one is that they couple very strongly to light. So they have very large resonances, so that you can use light to excite them and control them. And so they have very large optical response. And two is that they are this composite boson. And so that you could actually have very large interaction between them. And this nonlinear interaction is going to be something that be the focus of today's talk. And how do two excitons interact? For example, right, so like they are, these excitons have a electron and a hole, and they bond together as a pair. So one type of interaction like you could have are these sort of exchange type interaction. For example, you can exchange your electron or your hole. And you can also have exchange of the exciton. So you have this exciton-exciton exchange as well. So the exchange interaction tend to be sort of shorter range, so they rely on the overlap of wave function. And you can also have longer range interaction. For example, like the type of exciton that we are very interested in, one of these is called interlayer exciton, where the electron and hole are residing in two different layers of this 2D material, so that they would have a permanent dipole. So that you could also have these dipolar interaction that are much longer range. And these nonlinear interactions are very important because when you think about that, one of the hardest problem in physics is many-body problem, right? So that if you can control this type of interaction, you could potentially study many-body problems by using them to simulate different type of phases. And of course, like computational is almost like this is like the mega for these some of these type of approach called quantum simulation, and the most successful platforms are the ones that have been developed here are these co-atom trapped in optical lattices. And in that system, as I mentioned, like because this many-body interaction problem is so hard that you cannot solve them using a conventional computer. So one of the ways that you would be able to kind of look at what happened in this kind of problem is to do a simulation. And what type of many-body problem can it be? For example, if you have many-body interaction of electrons, you can get, if they have the right kind of interaction, you can get to things like superconductivity, for example. But superconductivity has been notoriously hard problem in condensed matter, right? It has not been actually fully understood. And one of the ways that you could want to understand this is like you can use these atoms and trap them into optical lattices, and then use this as like an artificial lattice to mimic your solid-state system. So each of the atom now you can think about them as sort of like a mimicking a electron, and you can tune and have very, very fine control of the layer interaction and look at the phases of this, what it arrives. And this is one way to kind of understand how these many-body interaction lead to things like superconductivity, right? And atoms are very suitable for this because they are very controllable by a lot of these methods that developed in this particular building. Like you can trap them in lattices, you can control their interaction, you have many knobs to tune. And also atoms are very, very coherent. So like the time scale you can have are, basically infinite to some extent, compared to other systems. And I guess the problem, though, is to some extent is that because essentially by enlarging the distance between atoms from like nanometer or subnanometer in the solid state lattice into something like half a micron in the gas phase, your interaction is very weak, right? So your interaction is very weak. That means that you have to go to very low temperature to study these phenomena, and this is why these atoms usually have to be cooled down to very, very cold temperature, like millikelvin or nanokelvin. And then the other thing I think is somewhat still is that, in solid state system, you have much stronger interaction. And also you have other dissipated pathway, like such as coupling to phonons. And this is hard to do in atoms. Like you can not actually easily to have actual phonons in these optical lattices. And so we have been thinking about like whether or not we can use solid state system to understand solid state system, and using Exciton as quote unquote artificial atoms and try to understand some of these many body interaction. And I should mention that I don't think the excitons are going to replace atoms. They are totally, as I would mention in my talk, they are going to be in very different regime, like are stronger interacting. They have much faster natural time scale. But then you can start to really think about the actual complexity of solid state, such as dissipation, coupling phonon, and so on. So this is kind of our initial attempt of trying to do this thing. That's what I'm going to show you today. And one of the things is that how do you actually study these phases, right? How do you know the phase that you have? And one of these ways is also pioneered in people here is like you can image these atoms, right? In the atom community, you can image where these atoms are, and it tells you a lot about what state they are. Like for example, this is an example of Colloquium BEC that was done here, and it was a Nobel Prize, of course. And in first looking at these collective phases, and so like if you could image these particles with basically unlimited or like absolute time and spatial resolution, in some ways you would know everything about that system. And some of these very successful tools in the atom community has been this quantum gas microscopy. And again, this is because now you trap these atoms in these optical lattices. They're about half a micron apart. Now you can actually look at fluorescence from each atom, and you can know exactly where they are. So for example, this is the example of showing a collection of atoms undergo a phase transition. And this is basically a lattices of atom, and then you have strong interaction between on-site interaction. So if you want to try to put two atoms on one side, they will strongly repel each other in such a way that the energy favorable condition in the high density would be exactly one side, one atom. And they would not move. And this is known as the Mott insulator state. And if you either reduce the density or like lower down this interaction strength, then they will, this atom will prefer to move around, and this is, you go back to this Bose-Einstein condensate or superfluid phase. And the way that people can understand these phases is by mapping where these atoms are as they changing the density of the atoms. So initially, at a very dilute limit, you have BEC, so you have this atom just kind of freely moving around. But as you increase density, you start to get to this crystal of like thing where the atom just localized one per side, and you get to the Mott insulator phase. And so this is, if you would look at the distribution of this atom as function of psi, you would see this like pancake-like distribution, right? So our inspiration then is that, well, how do we understand these quantum phases of this exciton arising from many body interaction? Then what we want to do is an analog of those quantum gas microscope measurement, where we want to be able to trap the excitons as function of space and in time and where they are. And it is a little bit harder to track the excitons. For one, is because these excitons are non-equilibrium state, so they are excited state of your material. So they have lifetime that's and dynamics that on the orders of femtosecond, nanosecond. So you don't have the luxury of the atom that they will just live there forever. So you need some kind of ultra-fast time resolution. This is why we need ultra-fast lasers. And then 2 is that in this solid-state system, the distance between excitons are much shorter. They are not half a micron. Again, because we wanted to induce this stronger interaction, so what that means is that it's harder to get single exciton spatial resolution. And right now, our spatial resolution is on the orders of 200 nanometers, which is still a collection of excitons. It's not a single exciton, as I would explain. But I would kind of try to convince you that even with that caveat, then we can still track where these excitons are collectively and understand their phases. And more importantly, like now, we can actually do these measurements at low temperature. Of course, it's not nanokelvin, but these are in a cryostat, so we can do this measurement at a temperature as low as 1.5 Kelvin. And the key thing about the successful of this measurement is that you need very high temporal and spatial precision and with high signal to noise. And the way that we track where these excitons are using this method called pump probe. So we have 2 ultra-fast pulses. One is called a pump, which is coming in to photoexcite. So that's what you create the exciton is. And the probe is as like an imaging pulse that, and coming in to look at where those excitons are. So, and we can do this in different ways. We can scanning the pump and probe relative to each other, or we can use a focus pump and a wide field probe to look at where those excitons. So, anyway, so then I'm going to start with from an example that is in the classical or semi-classical limit, where this exciton just going to be freely moving around and diffusing around. And this is an example of exciton in a single layer tungsten diselenide. And so we are just imaging at the exciton resonance. And in this case, it's about 2 electron volts. And at 0 time, what we see, and the scale bar is 1 micron. So at 0 time, basically, what we see is like the pump image where you injecting the exciton density with the pump. So it's a Gaussian pulse around half a micron in across. And as time progresses, you can see that these images broadens out. And this is because the exciton has migrated out from where it was created. And then if you take slices of those images, what you're going to recover is like this series of Gaussian. So at 0 time, the Gaussian is mostly defined by the pump. At later time, this Gaussian is coming from the diffuse motion of the exciton, right? So this is, if the exciton is purely diffusive, then the solution to this diffusion equation just give you a series of Gaussian, and the diffusion constant just given by the variance of Gaussian as function of time. So the slope just gives you a diffusion constant. So in this case, this is just like a single particle picture, assuming there's no interaction between this exciton and they just diffusing around, and we can image where they are. So now, how do we get to this strongly interacting case? And then to do that, then we need to basically engineer a lattice for this exciton so that we can study that correlation. And the way that we do this to increase the interaction is by using this Moiré superlattice. Basically, it's a bilayer system, and in this case, it's a single layer tungsten disulfide on top of a single layer tungsten diselenide. And because these 2 lattices have a 4% mismatch, then what you essentially create is a new superlattice, and highlighted by this green dot. These are the new superlattice. And then, as you can maybe see, is that in this green dot that I highlighted, which is a high symmetry point of this new Moiré superlattice, the hexagonal are right on top of each other. But if you move away from it, the structure changes, then the hexagonal is slightly offset. And what this does is actually creating a spatially varying potential for the excitons. And what you now have, instead of this exciton, it's just freely moving in the in a single layer, what you create is a trap for the exciton at certain location of the lattice, and now your exciton are trapped in this lattice, sort of very similar in a way of like how you use optical lattice to trap the exciton, to trap the atoms. And the reason that you want to trap them into the Moiré superlattice is that you want to make the exciton move slower, right? Because as they move slower, they interact more strongly with each other. Just as if like you are moving very, very fast. If you run really fast, you're not going to pay attention to people who are on the sidewalk. But you're forced to kind of move around like very, very slowly. You would have to interact more with the people around you. So this is the same way for this exciton. So like we're going to force them to interact more strongly by reducing the bandwidth or making the band flat, right? And so because of the Moiré lattice, now you kind of reduce the J, which makes the exciton more localized. Then the J is defined by the tunneling between sites, between Moiré sites. So now if you, this is a calculation done on this Moiré superlattices, and now you look at the exciton bands, then they become very flat. So this in condensed matter is known as flat band physics or strongly correlated physics. So then now you, instead of this parabolic band that these excitons are moving very fast, they have much slower motion. And that now, this is you started to get into the strongly correlated regime by then you can think about like realizing a simple model like Bose-Haber model using this exciton, right? So now I trap this exciton in this lattice, and the two parameters that's going to be important in this Bose-Haber model is one is the tunneling, which I already mentioned. Two is the interaction. So now the question is how strongly is the interaction between two excitons if I force them into the same site. So that's known as the on-site interaction. So as I already alluded to in the coatom case, if like you have, in the case of the interaction is much stronger than J, then you're going to enter a Mott insulated state, which is this exciton would not move around. And if the opposite limit, if U is much smaller than J, you're going to be in the other regime called superfluid regime. So, and of course, like this strongly correlated state have been widely studied in this Moiré lattice. In fact, this is one of the hottest topics in condensed matter physics in the past 5 years. And but mostly, these strongly correlated states have been realized mostly are the strongly correlated electronic states. So these are the fermions. And the reason for that is because in condensed matter, it generally is much easier to do transport measurement on electrons, because excitons don't really conduct current. So a lot of this traditional method of looking at transport would not work for excitons. And so that's why I think most of the work in the field has been done on these strongly correlated electronic states, where you can just using conventional method to look at electronic transport. And for look at exciton transport, then you would need different kind of method, and this is what we are doing. And also another key difference is that you know, exciton is an inherent non-equilibrium state, and so like how does the dynamics of exciton are going to affect these quantum states? And I should say the first evidence of some of these strongly correlated exciton states come from Chen Haojin's group at UC Santa Barbara, where they did a clever pump probe spectroscopy in just steady state, no spatial resolution. But anyhow, they're basically looking at what is the extra energy you need to put if you already have a layer full of exciton, and what happened when you're going to put in a second layer. And they have basically in this measurement show that U can be very, very large. So hence you have this sort of Mott inserted state. Oh, I already showed this. Okay. So in order for us to image these exciton phases, we have a collaboration with Professor Xiaodong Xu's group on this twisted bilayer twisted tungsten sulfide tungsten selenide system. And the reason is that one of the things that in order for this measurement to be successful, you also need this material quality to be very, very high, because you don't want the other energy scale come into play when you're trying to look at U versus J and others. And Xiaodong's group by far makes the best sample. So anyway, so we this is a sample on twisted tungsten sulfide, tungsten selenide, where the lowest exciton state is this interlayer exciton, where the hole resides on the tungsten selenide layer and the electron is residing in tungsten sulfide layer. So first we want to do some spectroscopy to characterize what is the energy scale in the Bose-Haber model. And what we did is we first did a steady state PL measurement where we look at the exciton emission as function of density. So at very, very low density, we basically only see one single emission band, which coming from the interlayer state. As we fill this exciton beyond 100% or like a fueling factor of 1, then what we start to see is a second energy emission, high energy emission emerges. And this energy difference is have to do with like when you force two exciton on the same side, there's going to be a strong repulsion interaction. And the reason this strong repulsion comes from that in the Moiré side, you restrict the conformation of this exciton. So you cannot actually form a bound state of bi-exciton, for example, because they cannot rotate, right? So this strong repulsion coming from the strong confinement of the Moiré lattice. And so now we know that this repulsive interaction is quite strong. It's about 40 MeV. And then we also then look at in the lowest exciton peak as function of density, it also slightly blue shift. And this comes from the second interaction type of this exciton coming from this longer range dipolar interaction. And this longer range dipolar interaction is weaker than the on-site, but it's still quite strong on the order of 3 MeV. And the tunneling is quite a bit smaller, about a few orders of magnitude smaller. The estimates here are coming from our diffusion measurement at a very low density, and that is probably the lower bound, but the upper bound, I would say, is still probably on the orders of tens of micron electron volts coming from theory calculation. So now then we have this exciton sort of like in this extended Bose-Haber model where you have a very strong on-site interaction and relatively strong dipolar interaction and much weaker tunneling. So we should be strictly in the Mott regime. And then we can also look at the dynamics of this exciton. So then we can, at the low density limit, the single exciton, these are interlayer excitons, so they have pretty long lifetime. They are about 40 exciton. I mean, compared to atom, they're still very short. But compared to other exciton, in the single exciton limit, if we just look at this lower energy peak, the lifetime is about 150 nanoseconds. And if we look at the higher energy peak that come from the double occupancy of these Moiré site, the lifetime is much, much faster. So is about a few nanoseconds. And this is coming from that if you have two exons on the same site, they also undergo this exon-exon annihilation, and this is much faster. So so we can also dynamically separate these two type of situation. And so in order to know whether or not like we actually realize a exon Mott insulator, like the way that we're gonna look at is whether or not the exon distribution at high density becomes this pancake-like, right? Because like, and also if the exon motion would stop, because that's what the Mott insulators they would tell you, because as you enter the Mott regime. So to do that, then we do this measurement of looking at the emission. This is actually PL imaging. So this is lifetime on one axis and space in the other axis, and as a function of exon density. So then what we plot here are the mean square displacement of the exciton as function of time and as function of exon density. Oh, yeah, I should mention all these measurements are at 4 Kelvin. Yeah. At a very low limit, like when you very dilutely fill this lattice, like say 5%, what you see is this exon just slowly diffusing around, right? So kind of like what I showed earlier, like in the diffuser regime, you will have the mean square displacement that is linear with time. So you just see a slow diffusion of this exon at the low density limit. And as you increase density, something very interesting happened is that this mean square displacement started to have plateau. It no longer changes with time as function at early time. So it's totally stopped. The exon motion stops at high density. And And after like tens of nanoseconds and some motion resume. And also if you look at the this kind of spatial distribution, initially you're going to see it just looks like a Gaussian-like distribution. At high density, you also start to see more like a pancake-like, the square wave-like distribution. And to show you like kind of this pancake-like distribution more clearly, I want to show you like this 2D imagings with a higher time resolution. And now this is just imaging the absorption rather than emission, so we can actually have time resolution on the orders of 100 femtoseconds. And so what you can see at low density again, you kind of just see this Gaussian-like beam just slowly spreading. But at a high density regime, things are drastically different. First of all, it spreads very quickly initially, and also it no longer is Gaussian at later time, right? Because a Gaussian will always have a highest density in the center. And you can see in this, as it progresses in time, you can see the center becomes dark. And if you extract some of the spatial, one-dimensional spatial profile from those images, what you can see is that initially you have a Gaussian, because that's what your pump is. But then as time progresses, you started to become a square wave, and you have these kind of edges as well. And the reason you have these kind of lumps, or like two lumps on the side, has to do with the limited spatial resolution of our imaging system, actually. Because the edge of this state that we created, Mott state that we created, are quite sharp. It's below our diffraction limit. So the diffraction limit would be, what have is that it convoluted with the kind of the spatial beam. And that's, so you can deconvolute it, and you can see that then you start to go from a Gaussian-like distribution to a pancake-like distribution, which, again, this is like what you expect from a Mott state. And then, so I'm just going to summarize like what kind of phases that we see in this measurement. So if we look at the MSD as function of time, and what you see are like these 3 different time regimes. Initially, it actually changed very fast, so everything's moving very fast. And that's because initially we create a very dense exciton cloud in the middle, and they are so dense that they are have strong interaction between them, so they kind of float above the Moiré lattice, so they're expanding very quickly. And then they will find on the edge some empty site to go into. And then at some point, once they do that, then some of the site in the center will more likely to be left with 2 excitons in one side. And so the initial expansion very fast is coming from this part. And then as I show you that the 2 excitons have very rapid annihilation loss. So after the annihilation concludes, then you're going to enter this Mott regime. That's where you see the motion of exciton is totally suppressed, right? So this is when you're in the Mott state. And then if you wait long enough, because these excitons have lifetime about 150 nanoseconds, if you wait about like 80 nanoseconds or so, you start to lose enough excitons so that your Mott state have a lot of defect in it, and then you start to resume this motion again. So you actually do see 2 phase transition. One is like when you form this Mott state, and then the other Mott insulator state, and then the other is the melting of these insulator states. One of the things that are very surprising to us is that these Mott states actually last for 18 nanoseconds, which is a very, very long time for an exciton, because these excitons don't usually, a lot of things can happen in the solid state lattice. You can have phonon, you can anything, a lot of things can destroy this coherence between these excitons. And so one of the questions was that why these excitons can stick together for 80 nanoseconds. So this is a question that we then return to our theory collaborator, Dante Canis. And Dante can do this sort of DMRG simulation, many body simulation, and looking at how this Mott state behaves. So what he did was that he first then created a Mott state, and he run 2 cases. One is without the long-range dipolar interaction. The other is with the long-range dipolar interaction. So it turns out that if you don't put in the long-range dipolar interaction, because this because our sample is actually about 10 microns, and our beams are about half a micron or so. So you always have edges that are still empty. So if you don't have long-range impulsive interaction, like a dipolar interaction, this exciton would quickly just move out to the empty side on the edge. So your Mott state will form, but it will melt very quickly. But if you now, interestingly, if you start to dial in dipolar interaction, then they stick much longer together. And this is because of this this energy scale of dipolar interaction is larger than the distance between energy difference between different Moiré bands. So these Moiré bands are very flat, right? So if your energy difference between these bands are larger than the dipolar interaction, in this case around 3 MeV, then it's very hard to dissipate those energy because, of course, you can always say, okay, let's phonon. But it turns out like it probably is because phonon scattering is slow at this very low temperature. So the conclusion that we got from the Dante's calculation was that this dipolar interaction, because the energy scale is still much larger than J, and also coupling to phonon, so it prevents, kinetically preventing the melting of these Mott states. Okay. Yeah.
Have you measured the temperature dependence of this lifetime?
Yes, we did. It becomes shorter, yeah.
How fast does it become shorter with temperature?
So at 80 Kelvin, basically it's no longer holding it. Is in the supplementary in the papers. But it basically by, of course, the lifetime of exciton also becomes shorter at 80 Kelvin. So those are two things, right? So they are, anyway, so then the question is like, okay, so we know now we can see this Mott insulator phase. What about superfluidity? Can we also get to that phase? And it turns out it's actually very hard. And the reason is because in the Moiré TMDs, in order to get to the U is smaller than J, you could get that, but then your disorder becomes much more important, and your disorder kind of dictates your physics. And this is part of the reason that I think some of the things that are harder for the solid state system compared to atom is that you still have to deal with a lot of this messiness of real materials. So okay, so the way to get to a superfluid phase is that you could have to get to J is greater than U. The other thing that you might ask me, like, well, shouldn't you also have superfluid when you are way underloading your lattice, which is like the 5% case? Why didn't you get superfluid? And the reason is, again, like the J is smaller than probably than thermal fluctuation or other scattering channels. So like we actually just see diffusion, not superfluidity. And so the quest is that what we're trying to do is to get to this phase of like, having this exciton as if like there's no scattering. And I'm going to skip this slide. And the way that we have our attempt at it is trying to utilize both the exciton interaction as well as exciton and charge interaction. And so the idea is such. In this two-dimensional material, you can also easily dope in charges. And in fact, this is like, how people realize strongly correlated electronic states. And that imagine if you can have a charge order, and on top of that, you create exciton order. And the charge and the exciton, if they have strong interaction, and in this case they do, then your exciton would also have to be pushed up to occupying a higher energy states. And in this case now, we're going to look at a exciton lattices that is kind of elevated by the charge orders. And in this case, we hypothesize that when they occupy this high energy state, then they would have a larger J because then the potential is smaller. And there's also some theory have calculated show that you can get to a larger J when the exciton are occupying the high energy band. So this is what we're trying to do. And so in the same sample that I show you, now I'm going to not just looking at exciton, but also I'm going to look at charges. So this is a photoluminescence now as function of doping into different density of a charge. And now what you see is that the exciton emission intensity change quite abruptly at certain fractional filling of charge. For example, at 2/3 filling. And this is well known actually because exciton have been using to sensing charge orders. The reason exciton can sense that is because the dielectric screening is going to change when your charge crystallizes. When your charge is no longer moving around, then the screening is going to be much weaker compared to when it's moving around. So this is just a pretty well-known thing already. So if we take the derivative of this, what we can see is that you can see all these different special location of the charge orders, like 1/5, 1/3, 1/2, and 2/3, and so on. And but also what's more interestingly is that we now can also see a new emission, for example, near the 2/3 filling. It's slightly higher energy than the lowest exciton band, and we think that this is coming from when the exciton has to co-occupy with charge. And because of repulsive interaction between them, they would also have to occupy a higher energy. And then we can look at the dynamics of all these different species. Again, the single exciton, they decay very slowly. If they have 2 exciton, as I discussed, it already decay faster. If you have an exciton and a charge, it's somewhere in the middle. So you have slower than 2 excitons, but it's still faster than the single excitons. And now what we wanted to look at is how the exciton transport is going to change by these charge orders. And so we look at 2 cases. In particular, we are interested in the strongly correlated limit where you have very high density of exciton. So on the left, I'm plotting, this is just basically I prepare a exciton Mott insulator on top of the charge. And on the middle, I compare, in the case, I just very dilute excitons, so there's no correlation between excitons. And on the top row, I plot the lifetime, and on the bottom, I plot the transport, so MSD. So initially, like of the gecko, you can see which is that when excitons are strongly correlated, they're much more sensitive to charge orders compared to when the excitons are not correlated. So when excitons are not correlated, these changes seems to be more homogeneous or like monotonous. But if you look at the when excitons are correlated, you can see there are sharp changes around these charge orders. And the most obvious one is around 2/3. So I'm just going to explain that one in particular. So what you see at around 2/3, the lifetime becomes shorter. So blue is just low density, so it just means that it decays faster. And the spread of exciton, MSD, becomes faster because yellow just means higher MSD. So these exciton, when they are nearly correlated electron states, and when the exciton is also correlated, they have these very abrupt changes. And we can look at this transport more closely. So if I just look at one just right below the 2/3 filling, and one is right at 2/3 filling. And again, this is time, this is space. And you almost can immediately see that when they are at this critical filling, where the electrons are forming a crystal, the exitons spread out much faster. And also very interestingly, now if I plot the MSD as function of time, it's no longer linear. Linear tells you is diffusive. Now what we see is actually quadratic. And quadratic MSD comes from ballistic type of motion. And notice that the time and the speed of this ballistic motion depending on the density of the charge. So it's the most enhanced at 2/3 filling. And if you go beyond that or below that, it all reduces it.
You're still talking about the interlayer exciton.
Yeah, this is still interlayer exciton. But now I artificially push it up by the charges. So like when they co-occupy with a crystal, the exciton have to occupy a higher higher states. And the reason why the crystal matters is that if the electrons are not crystallized, they just kind of flushing around about, and then so that the interaction between the exon and charge will be less.
But what do you do with the hole density? Is that just treated as sort of a continuum?
You mean the charge density?
The holes, yeah. So you're talking about this is the electrons in the upper layer, right?
No, these are exons. I'm just thinking exon as a whole. So like the yellow thing is just exon.
They move together.
They move together. Because the reason I think they move together is because the binding energy of exons are very large compared to all these energy scales. So I don't think they dissociate.
So it's the excitons that are forming the Wigner crystal, not electrons.
So the electrons are forming the Wigner crystal. And the exons are formed of Mott states, yeah.
You said it's micro-EV energy scale for popping of exciton. That's amazing. You can have that kind of order at 4K.
The microelectron world is this lowest exon band. We are thinking that when you put the exon on top of the Wigner crystal, this J is going to become larger.
The Wigner crystals of excitons, how is it different from a Mott state?
There's no Wigner crystal of exon here. It's just Wigner crystal of charge.
Oh, well, maybe I'll ask one. Okay. Yeah.
So I just flood exon everywhere. So exons is everywhere. The charges are in the fractional filling. So like what is also interesting is that, what's also interesting is that the correlation of exon is really matter, because if I just go to, like this is very low density of exon, but the same charge. My charge is still form a Wigner crystal at 2/3 filling. It doesn't change. But if I only have a diluted exciton, then this is just, the exon can freely hop around, so that interaction is also not as strong. So that you don't see in the low density exon limit, you don't see these abrupt changes at critical filling of charges. So then we can then look at extracting like the maximum diffusion constant as function of, this is somehow covered up, but this should be VE, so this is charge filling. So you can see in the high exon density limit, you can see that you can have these abrupt changes, but in the low density exon limit, you just have continuous change as function of charge. And the reason you have increased transport at low density is because just the charges screening increases, so you kind of just make the exon moves around more. Also, if you look at longer time behaviors, then you initial like the first 20 nanoseconds, you have this ballistic like drastic quadratic behavior, and at some point your exon also decay away, so that you also then enter this more diffusive like regime. Okay, so as you mentioned, that there's a science article just came out a couple of weeks ago, reporting somewhat similar, but in a very different regime. This also they did not address exon correlation. So these are at low exon density limits as well, and they do see an enhanced transport at mostly at nu equal to 1, which is the Mott insulator state of the charges. Okay, so I guess I'm kind of out of time, right?
Well, you go to 5, so you leave maybe 5-6 minutes for questions.
Okay.
Yeah.
Okay, so 5 minutes. So one last thing also about increasing interaction between exons. And in this case, we look at a much simpler system, which is a single layer. And the reason that we are interested in this is that, can we increase the interaction length scale of excitons? And these excitons, they are mostly, like composite bosons, so they come from, electron holes. And if you just think about like how over what length scale like interact, they are kind of only orders of nanometer, 10 nanometer at most, right? From this dipolar interaction that I mentioned before. And what are the ways that you can increase the length scale of that interaction? And previously, people have tried things like analog of Libai, like Libai exciton, but then Libai states are in solid states generally don't live very long. And the reason that we want to increase that length scale of interaction is that one is that you can control, again, like better control these many body states, as I mentioned. But also you can imagine if you can increase the length scale of interaction to the scale of a photon, then you can start to enter this single photon nonlinearity regime. These are important for things like quantum computing and things like that. And so one of the things that we can think about how we can further increase the length scale of interaction is by, again, involving the charges. And in this case, like people have shown that you can form this quasi-particle called Fermi-polar Huang, where a single exciton as an impurity interacting with a degenerate Fermi C. So in this case, you can have an exciton interacting with many charges and many fermions, and this fermion then can mediate the interaction between the exciton, and you can enhance interaction level. And so people have shown that you could indeed increase interaction level, but it's unclear on what length scale you can really increase that interaction. So in some of the more recent work, this is a collaboration with Tony Hines' group at Stanford and Valentin Waters' group at Purdue, is to really try to understand what is this length scale of interaction and whether or not we can enhance using Fermi C to mediate this kind of interaction. And so what you now see, this is just a single layer MOSE2, and now we can dope into charges and at different density. And what you now see is a splitting of this exciton resonance into one is known as the repulsive branch, and the other is the attractive branch. And this is coming from this many body type of states. And Valentin's group have done calculation on the wave function of this polar and show that you could indeed have exciton interacting on the length scale of a few nanometer, depleting charges from a length scale that is larger than exciton itself. And I know I don't have a lot of time, so I'm going to cut to the chase. One of the things that what you expect is that if you indeed can reach much larger interaction length scale, one thing that one of the signatures you can look at is how much nonlinear it becomes, right? This exciton becomes with charges. And nonlinearity can be measured in this pump-hole measurement I just mentioned. But in this case, what you want to look at is that if linear absorption, which is the pump-off black line, how much that can be modified when you have on a pump-on condition, which is you already generating multiple excitation, and look at the linear absorption with the other excitation around. So if you have very strong nonlinearity, then you can totally saturate out this transition. So at polar, what you see is that at the same injection density, about 10 to the 12, you can see for the bare exciton, you barely change the reflectance spectrum. But in the polar, you actually almost 100% quench that transition. And this is coming from that once you create an excitation, this polar, and they're large, you can no longer on the same space to put another polar on. And this indicated that the length scale interaction is much larger than the exciton alone. And we can also spatially image it, right? So like we can look at also in the exciton, spatially, this nonlinear response restricted to area where you pump it, but for the polar, it's much, much more extended over a few microns. So I don't have much time. I'm just going to say then we can extrapolate optical nonlinearity by looking how this transition saturate, and the polar saturate at a density that is 2 orders of magnitude lower than the excitons, and from that from that, what you can extract is from this nonlinearity curve as function of density, you can extract what is the blockade radius in this case, and it turns out to be about 30 nanometers for the polons, and in comparison for about 1 nanometer for excitons. And this, again, is coming from these Fermi seas mediating this long-range interaction between the excitons. And those measurements are, again, done at 4K. And what happens if you increase temperature, then you increase the line width of the polons, and so that the interaction you would need would be much stronger to create this blockade. So at higher temperature, you will see the shrinking of the blockade significantly for the polons. So I want to save some time for questions, so I'm just going to end here. And want to say, I hope to have shown you that thinking about these many-body interaction of excitons, we can really try to start to think about how to address many-body problems in the solid states. And with that, I want to thank my student who did all this work, and mostly by a very talented student, Jonas Peterson, and a former postdoc, Shibing Deng. He now is a professor at Nankai. And I want to thank you for your attention, and happy to take questions. Yeah, that's a very, very good question. And yes, we are in the process of looking at that. But we expected to look at some of these other type of phases that can arise from a spin. Yeah.
Quick follow-up: what was the rationale for choosing your 60-degree R-type stacking for the heterostructure?
Versus
0 or 180 degrees.
Okay, yeah. The reason is because for the 0-degree stacking, the Moiré trap is even deeper. So the U is even, so like you trap, you can trap up to 3 excitons. And it's just more complicated in terms of exploring these phases. It's easier for us to just look at the 2 versus 1. Yeah.
Can you make the exciton dilute enough that you can do imaging on individual excitons?
Yes.
This is a very intriguing possibility of radiation blockade and so on. In order to do that, if we want to turn it into qubits, you want to be able to control individual excitons.
Yeah, this is kind of en route to some of these goals that we're trying to do. Yes, absolutely. So in the Moiré case, you could use other way to generate Moiré, like for example, like twisted HBN can give you larger Moiré distance, and then there's also fabrication technique. I think that formally, if you just wanted to image single exciton, that's no problem. You can do PL, that's sensitive enough. The key thing is that how do you enable still strong interaction with large distance? I think that's hard. And the other approach would be something like what Markus does, which is go beyond the far field limit, go to a near field, and you can you can go beyond like diffraction limit. So you can go to the tens of nanometer scale. So those are kind of things, we are trying as well. And in the last case, like how you get to single photon nonlinearity, those are going to require some nanophotonic cavity to confine line into tighter space. Those are kind of some of the things that we are currently working on to combine this polon into some nanophotonic devices.
You're, let's say, looking for superfluidity. You'd like to have everything very cold, but then you're driving everything by using photons. Those photons heat your system as well.
Yes, it does, but it usually doesn't heat it up by more than a few Kelvin, and that's in our estimate, and in probably less than that even for a lot of density that we use. This is kind of like the regime we work on 4 Kelvin, 6 Kelvin. So it doesn't matter for the states like Mott states and so on. But it would be probably more problematic when we're trying to go to some of the spin state that was mentioned earlier. Like those transitions tend to happen at much lower temperature, and then that would probably become more of a problem. And yeah, I don't know how to overcome those yet. Probably we have to see what are the theory prediction and what kind of temperature we need to be at. Yeah.
The last few slides where you had this was this exciton polaron.
Mm-hmm.
Right? So this is just an exciton polariton, or is this an exciton lattice? So what was your definition there?
Is a Fermi polaron, so it's just kind of